Yes, thanks. So I'll talk a little bit about singular structure and classical general relativity, what kind of metaphysical perspectives we should have on it, and in particular, my main claim would be that singular structure in classical general relativity is best conceptualized as an extrinsic, non-local, but localizable property of space-time regions of any size, but sufficiently structured to be represented by an open set at least. And there is no unique best definition of singular structure in GR, but there is a schema that any adequate definition should instantiate. And actually, what counts as an adequate definition is related to what counts as a physically reasonable motion for an observer in general relativity. Health warning, I'm just going to talk about classical general relativity. I'm not going to say anything about quantum gravity and what kind of impact it might have on singularities. And so I'll start with a review of relevant technical facts. I'm very happy that the previous speaker has said some things about GR, so maybe I can be quicker then. The second thing I'm going to talk about are various conceptions of singular structure, what kind of conceptual perspective we should adopt in analyzing it. Then I'll discuss the notions of locality and localizability as applied to properties of space-time or space-time regions. And at the end I'm going to provide the definition schema for various definitions of singular structure and say a few words how this definition schema gives us reason to believe that singular structure is an extrinsic property of space-time regions. So I say possible physical spaces in general relativity are represented by Lorentzian manifolds. I have an mg. If you put your Einstein field equation glasses, you'll see that the T hides behind the G. So I don't have a T explicit there, just mg, but no worries. M represents the space-time manifold, G represents the geometry of space-time. The matter content can be uniquely recovered from G using Einstein field equations. There is a sense in which the metric G can be in various senses singular, so you might come across the difference between coordinate and curvature singularities. You've seen in the previous talk, those who've been there, the expression of the Schwarzschild metric and Schwarzschild coordinates. If you put these coordinates onto a space-time describing a non-rotating, non-charged black hole, you will have a coordinate singularity. The metric in these coordinates won't be well defined for a certain value of r. But it turns out that's because the coordinates don't describe the whole space-time manifold. If you make a coordinate change, you will have a well-defined metric at that point. That's kind of coordinate singularity. As opposed to this, you might have curvature singularities. So you might have a certain curves in your space-time along which some curvature scalar grows indefinitely. You have this also in the Schwarzschild case. For r equals 0, there will be a genuine curvature singularity. The Kretschmann scalar will diverge. Now, these curvature singularities are always witnessed by incomplete curves of a certain kind, curves that are inextendable and also have a finite proper time or affine parameter along them, and along which these curvature scalars diverge. But there are also, and people just say then that it means that the singular structure of space-time is witnessed by such incomplete curves. But it's also the case that there might be incomplete curves of this sense along which all the curvature scalars are well behaved, and along which also all the components of the Riemann tensor and any frame that you parallelly propagate along these curves are also well behaved. The simplest example is something like a Minkowski spacetime with an excised origin. I mean, all the geodesics that would cross the origin just end at that excision, really. You might think that's a bit artificial, but there are less artificial examples of singularities like this that seem to be genuine manifold singularities, though not necessarily curvature singularities. So, the kind of standard story is this: singular structures witnessed by incomplete curves. It seems that we can't just check any curves that are incomplete to witness singular structure. There must be some further principle we want to comply with or be motivated by, and I think the answer that I endorse, and you can also see in some physics literature, especially in the late 60s, where people were very excited by this stuff, is that singular structures witnessed by curves that disrupt physically reasonable motion in some sense. A popular answer was that it's both a sufficient and necessary criterion for singular structures that there be incomplete time-like or causal geodesics. And these are the kinds of things that are proved to arise in generic solutions by Penrose and Hawking and Penrose. And incomplete, as I said, it means of a finite affine parameter and without endpoint. And without endpoint also just means the same as inextendable. The trouble with that is this sounds like a sufficient condition for singular structure, but not really a necessary one, because surely not all physically reasonable motion is freefall. And there are examples of spacetimes where all the geodesics are complete, but there are curves of bound acceleration which are incomplete. These kind of examples were given by Garrosh in late 60s. So an alternative would be to say, oh, maybe the spacetime is singular just in case it contains incomplete causal curves of bounded total acceleration. Another more permissive idea was to use the notion of B incompleteness, which is strictly weaker than bounded acceleration completeness and geodesic completeness. So there was this idea to define this special parameter called generalized affine length, which the idea was basically just integrate over squared components of tangent vector relative to a parallelly propagated frame field along the curve. That's a frame-dependent definition, but what's fortunate is that whether this parameter is finite or not is frame-independent. So you could say that a certain curve is B incomplete just in case there's a finite generalized affine length and no endpoint, and the spacetime is B incomplete just in case it has any B incomplete curve. There are some relationships between in what cases curves of finite proper type also have finite generalized affine length. It turns out if you have bounded acceleration and finite proper time, you will have finite generalized affine length, and you also might have unbound acceleration, but it can't really kind of grow too fast. There is a particular condition on how the acceleration is to be offset by the remaining lifespan of a curve. So the moral is this: we do have two proposals, this bounded acceleration, B completeness. How should we decide which of them provides really a necessary condition for a curve to count as witnessing singular structure? Must acceleration, total acceleration be bounded for physically reasonable motion, or is this kind of bound on growth sufficient? I'll stay agnostic. You can ask me about Q&A maybe more, but the kind of thing I want to say is there is a spectrum of good candidates somewhere in between those alternative 1s and 2 for what kind of curves give you both a sufficient and a necessary condition for a curve to witness singular structure. Okay, so this is kind of a review of curves in spacetime. Another thing which is important to mention is people in late 60s and 70s, especially later on a bit less, had this idea that even though space-time itself does not contain the singular points, it would be nice to have a mathematical construction which would add those points on top of our space-time in a way which would allow us to kind of understand better from a mathematical physics perspective what's going on at the singularity. And these go under the name of boundary constructions. So you can have you see a list there of various of these boundary constructions. But it turns out that there is quite a general theorem which tells you that if you have a certain boundary construction based on some form of curve incompleteness, and it satisfies certain quite mild assumptions, we'll talk about them later, this proposal will feature some topological pathologies. And in particular, you will always have it that a point on the boundary would no longer be topologically separated from points in the interior, which results in facts like, well, any smooth scalar field defined on the whole space now with the singularities can only be constant, which makes it very useless. That was a result by Garrosh, Wald, and Chambin in 1982, and after that, the research on the boundary proposals really shrinked. Though more particular cases of those topological pathologies were known earlier. So boundary constructions, bad. Okay, so this was the review of the technical stuff. Now we just take a step back from those technicalities and we can ask ourselves, okay, so what are singularities supposed to be? What is our conception of singularities in GR? What kind of conceptual motivations we might have to pursue this particular mathematical construction or that particular mathematical construction? So the first kind of thing I want to settle is first kind of ontological distinction. Should we think of singular structure as instantiated by objects, singularities, or should it be something like a property of space-times or space-time regions or something else perhaps? So singularity is a noun. I use the word singularity all the time. That suggests I'm talking about like an object. It's not great reasoning. The concept force is a noun phrase too, right? Doesn't designate an object. We had Frege in the previous talk too, so I don't feel bad. We shouldn't be misled by language. I'm going to now talk about singular structure to be somewhat kind of ambivalent between these two ontological categories. And we have a distinction from John Ehrman from 1995 between the nominal and the adjectival conceptions of singular structure. And the nominal conception is precisely that singularities are objects. They're not material in the sense that they're not located in space and time, but they're physical in some sense. But they're not abstract either. And Ehrman quips that they exist with the universal quantifier. Good job. Then you have the adjectival conception, which is to say that is singular denotes a property of spacetime, but strictly speaking, there are no objects that one could properly name singularities. It's just a loose talk. And this is something that has been really accepted after the failure of the boundary constructions, because people thought, well, we have no good means of mathematically showing what kind of objects singularities could be so that we could actually do some kind of mathematical physics about them. So we'll just say, yeah, space-time is singular just in case it contains such and such incomplete curve. I think that's nice, though I do think we can really extend this adjectival conception and say that is singular might be a property of space-time regions, proper space-time regions within space-time, not necessarily the whole space-time itself, although also a property of space-time itself in the limiting case. There is some intuitions behind this. I mean, people usually would like to say that certain regions of space-time are singular, other regions are not. Here I have a beautiful diagram of a Kruskal-Schwarzschild space-time. This is maximal extension of the Schwarzschild solution. You would want to say, oh, look, region 1 is certainly not singular, region 2 is singular, right? But you can't really treat those regions as space-time on their own and then apply a definition of singular space-time, because each such region as a space-time on their own would be extendable, and it turns out that every extendable space-time contains a time-like incomplete geodesic. So it would be singular according to any reasonable definition. So you need some kind of tweak to make sense of a singular space-time region that is a proper region of some space-time. I'll get to this. But one might say, okay, there is no clear mathematical criterion for determining whether any given region counts as singular. So fine, I'll try to give one. It's very elementary. And I'll call this the extended adjectival conception of singular structure. I endorse it. And so I say, singular structure in classical general relativity, best conceptualized as a property of space-time regions. Let's take one more step back and think what kind of even motivations we might for choosing one conception over the other. So one thing is, of course, the availability of mathematical explication, physical fruitfulness, and intuitive plausibility, coherence, certainly a good criterion. Against the nominal conception, it seems that we have no decent mathematical explication. The boundary constructions were a failure. It seems some people want to say that the nominal conception is still intuitively plausible. So Ehrman, for example, says that the nominal conception is arguably a touchstone of singularities in relativistic spacetimes. Space-time singularities correspond to missing points. Okay, why would anyone say this? It seems to me that one motivation is that there is a sense in which singular structure is localizable. When you move toward the black hole region, toward the r equals 0 in your Eddington-Wittgenstein coordinates or whatever, it seems that you're getting closer to the singularity in some sense. So you would like to have it localized somewhere. It's not like it's a totally global property of space-time. But the question is, in what sense is it exactly localizable, and is this sense available only to the nominal conception? I think it isn't. Another motivation might be that some physicists would like to be able to do theoretical physics at a singularity. The idea there is, if you have a well-defined mathematical model of a space-time with singularities, and you can do some mathematical physics, maybe you will recover kinds of relationships that would later inform how theoretical physics might look at those, well, high energy regimes insofar at least as your singularity is a curvature singularity, right? But it's not clear to me that this is coherent only in conjunction with the nominal conception too. I mean, in the absence of actual mathematical physics, it's just hard to say. So I would like to say, fine, let's keep the extended adjectival conception and now consider whether on this conception being singular is a local property and a localizable property, and how does this mesh with those intuitions that I ascribe to Ehrman and other people too. So there are different definitions of local properties of spacetimes or spacetime regions. Some of them are formal, those given by Eric Curiel, J.B. Manchak, Sergei Krasnikov. I don't want to talk about them in particular. The point is that on all of them, being singular on a kind of formal definition schema that I will give you comes out as a non-local property of spacetime regions, or a non-local property of spacetime. There are also informal definitions of what it is for a property to be local, given by Jeremy Butterfield, Vincent Lam, Jim Weatherall. On the first two, roughly local means associated with a point in spacetime. So clearly being singular is non-local in this sense. Now I'm going to turn to Weatherall's definition as a kind of stepping stone between locality and localizability. So for Weatherall, a property F is local, or Weatherall local, whatever, just in case it can be associated with some region of spacetime that is represented by open set with compact closure. I'll set compact closure aside. There are some subtleties regarding how relative compactness plays with singular structure. We might talk about in the Q&A. So I'll just now say that, let's say that there is a sense in which a property can be local if it can be associated with a region of spacetime, though that's ambiguous between A, determinable from the information given in that region considered as space of its own, and B, determinable for that region, possibly from information beyond that region in a way that's informative and maybe allows distinction between various regions. So this is really a hedge against saying a region is singular just in case it's a region of a singular spacetime. That's a bad definition. Informative, I'm going to get to that soon. So I think A is indeed a kind of a locality claim about the property of spacetime. I think B seems to indicate a bit of a different concept. There's no longer locality, but can be called localizability. So these are, I agree, fairly idiosyncratic ways of using this term, but I think it still can make sense in relationship to the intuitions I presented before. So the idea is plausibly one can discriminate between regions of a single spacetime that do not exhibit singular structures from those that do in some intuitive cases. You had the Kruskal-Schwarzschild, you can do the same with FLRW or whatever. And identifying a singular region, in fact, is a positive test for the whole spacetime to be singular. In this sense, this is an informative property, and it's localizable in the sense that, if I can say this particular region of spacetime is singular, I know the whole spacetime is singular. So compare this with, for example, some topological properties. Every spacetime will have both simply connected and non-simply connected regions. So if you see a region is simply connected, unless there's a whole spacetime, you can't tell whether the whole spacetime is simply connected or not, right? Here, that's informative. I think this deserves to be called somewhat. I think localizable is a nice name for it. So I think so far I tried to convince you that it seems coherent, at least to think about singular structure as a property of spacetime regions, but it's not quite that. It's a good story. I definitely should give you some kind of more precise explication of what it is for singular structure to be associated with a particular region. And so here's the kind of definition schema. As I said, it's quite elementary. You have for any relativistic spacetime, you have an open, I call it psi subset. Psi ranges over topological properties, just in case you want to be more restricted than being open. Maybe you want connected subsets. U of M is a phi incomplete singular psi subset of that spacetime. Phi ranges over different kinds of incomplete curves. So you might choose bound acceleration, you might choose B incompleteness, whatever you like. If and only if there is a psi incomplete curve or half curve from some parameter space to M, whose image is contained in U. So that actually works for the Kruskal-Schwarzschild example, it works for the FLRW example, has a number of virtues, I think it's simple, it's flexible. No silly misclassifications as far as I can tell, but if you do have one, please let me know. I think this fixes this physical-mathematical challenge to the extent adjectival conception in a way that meshes well with this pluralism about curve incompleteness discussed before. And it also makes it clear in what sense you might think that being singular is now an extrinsic property of space-time regions. So intuitively you could say that whether it holds of a particular space-time region depends on facts about space-time points that do not belong to it, right? Because to see that you do have a curve in your space-time region U, suppose it's a proper subregion of space-time, whether that's an extendable, you have to look at the closure of that region to see whether it can be extended at the points of its boundary, so to speak, right? So you do need to have information about points in the closure. Now, since space-times are connected, at least I assume that they are, it turns out that every proper subregion will have a non-empty, every proper open subregion will have a non-empty closure. So you do need to look at facts about points outside of that region to determine whether it is singular. There are many ways of cashing out the distinction between intrinsic and extrinsic properties. None of them favored by most, I suppose. I'm just going to look at, there's a case from David Lewis. There's a 1983 criticism of Kim's definition of intrinsic versus extrinsic. So it's pre-plurality of worlds. So there Lewis said that F is a positive extrinsic property if and only if F's instantiation by any object implies the existence of a distinct contingent object. So Kim thought that this is a good definition of extrinsic, but Lewis said, no, actually that's a bit too strong. But of course, positive extrinsic implies for Lewis extrinsic. So I say even in the strong sense of extrinsic, it would be the case that singular structure is extrinsic because, well, okay, you take a proper subregion of space-time M. If S is singular, then this implies the existence of space-time points distinct from those that comprise S, namely those that are on the closure. And that follows from M's being connected, as I said. So being singular is positive extrinsic. I mean, you can reject this if you maybe are a necessitist, so you think necessarily everything is necessarily something, or deny that space-time points in particular exist contingently. I still think that there might be ways of modifying your definition of extrinsic then that would make being singular an extrinsic property, insofar at least as it's a property of proper subregions of space. So this is just spelling out why I think being singular is extrinsic, using one particular way of specifying what is an extrinsic property. And I'll end with some kind of further questions with partial answers. So the first question is, does the definition schema generalize to other space-time theories? It seems so. I think nothing really depends on the signature of the metric, the fact that it's Lorentzian. I think depends on very kind of Einstein-filled equations or something. In other theories, some people argue that the notion of singular structure can be less ambiguous. Maybe there is a well-defined concept of energy that's frame-independent. And you could think that the physically reasonable trajectories are exactly those that have totally integrated energy. Second question is, can the definition schema be put to formal work? Can you actually maybe prove some interesting things using this definition schema? There are some preliminary results regarding connected B incomplete singular subsets. So one thing I've been thinking about is, if you have this definition schema, can you always show that the singular regions will be in some mathematically precise sense small? It turns out boundedness is not available because you have Lorentzian metrics, so you don't define a standard distance function. Relative compactness, another kind of topological measure for open subsets, is not quite available because sometimes the singular structure exactly disrupts the relative compactness of arbitrary regions. If you want to know more how to go forward with this, and I'm happy to talk about this in the Q&A. Third question, can we further educate between various candidates for psi? That is, different kinds of curves that witness singular structure. So bounded acceleration completeness versus B-completeness. There are some ideas regarding energy and total integrated acceleration that one might use. There are some arguments given by people like Garrosh, Chakrabarty, and Liang to the effect that every physically reasonable motion should follow trajectories of total integrated acceleration. I'm a bit skeptical about these arguments. We can also discuss them later. Fourth question is, are there alternative characterizations of singular regions of spacetime? I just said one. Maybe there are others, and maybe they're better. How do they compare with the one presented here? As far as I know, there are no in the literature. There might be one that's motivated by some discussion by J.B. Manchak and Bob Garrosh about the definition of singular spacetimes for extendable spacetimes. That doesn't make it trivial that they're singular. It's not endorsed by any of them, but you can consider it. I think it's less appealing than the proposal I give. And yeah, I think that's it. Thanks very much.
Next will that comes from Wüthrich.
Thank you very much. So, as I see it, the main contribution of the paper is that Frank makes precise sort of an old intuition about the singular structure, singular character of spacetime being localizable without being local in some sense. And, he gives specific proposal for that tries to make this more precise, which I think is very attractive and certainly deserves to be discussed. So thank you very much for that. I do have three points that I think are worthy of discussion among all of us, I guess, or for you to answer. And the first point is really maybe that's not in any way an objection to what you're doing, actually quite the opposite. It is a more general question about what it is that we do when we think about these singular structures in general relativistic spacetimes. Because there's an old point that's been made, that you did make as well, that's been made in the literature beforehand, namely that there doesn't seem to be a sort of a unified, completely monolithic, mathematically rigorous and precise conception of what it is to be singular that exactly gives us the necessary and sufficient conditions for singular structure. Many authors have noted that we can formulate a number of conditions which seem to be sufficient, such as, for instance, the being completeness condition, which is a very popular candidate for that, which many people accept as a sufficient condition, but I think nobody takes to be a necessary condition. And there's a number of other conditions you can formulate like that, and it seems to be a little bit like that. And then people are like, oh, you know, what it is to be singular is very complicated and very difficult and sort of, you know, falls apart. The question to me that I asked these people is that why in the first place did you accept or expect that our somewhat vague conception of being singular as in some way a mathematical failure of the formalism of our theory that really boils down to exactly one sort of concept that's precise and rigorous and mathematical. Maybe the mathematics can fail in some vague sense in a number of ways, and what we end up with is then sort of a disjunctive criteria, perhaps. A number of sufficient conditions altogether, you know, as a disjunction or maybe necessary for singular behavior, but none of them should be thought of as individually necessary. Anyway, maybe you want to comment on that, maybe not, but to me that's always a bit sort of puzzling what exactly is the concept or the project we're doing here. Now, I do think that there is, of course, value in trying to think mathematically rigorously about what could go wrong in different ways. Something could be problematic in those spacetimes. And I take it that it's uncontroversial that if we label something or identify some spacetime as singular, we mean to thereby express a form of failure. The mathematics fails in some way. There's something going to infinity or something really bad happening. And I noticed that on slide 2 you took out a particular characterization of the realism that you extended to singular structure that is, however, present in a later slide still. So an earlier version of the slide said that let's be realists about GR, that means we should be realists about singular structure, meaning that we should interpret it as some sort of genuine physical feature of the world. And I was honestly puzzled about that. Maybe you want to elaborate on that. I was puzzled about that because I think, yes, let's be realists about GR. GR is an excellent theory, but if GR itself tells us, I'm breaking down here, my mathematical representation really goes awry, don't trust me here, then that's exactly the kind of situations in which we should not be realists about it. Rather, is my point to some sort of interesting new physics that we need to develop and more fundamental theory that we may need. So the remnant of that view that I saw on the slides is something in the middle of the talk, maybe about slide 12 or something like this, where you said this is an important project because we want to know how to do physics at the singularity or at a singularity. Yes?
Yeah.
Why do we need to do that? I mean, it depends on what you mean by the quote here exactly, I suppose. But I think, maybe the sort of a flat-footed realism isn't quite sort of the right attitude to have here. So I'd like to invite you to comment on that. And then the third point, I'm not going to, so there's a lot more in the paper about the third point I want to raise about your own original proposal, which I think is very interesting and promising, so for the record. In the paper, you do argue more at length that it gives at least 2 advantages over other characterizations that one might come up with, which are inspired by the work of J.D. Manchak, even though they're not endorsed, as you rightly said, by him in this form. And the 2 advantages you claim for your conception is first, that there's no strange or silly, I think you call them silliness characterization, misclassifications. And here I just have a little bit of a word of warning, namely that whether something's a misclassification or whether this is something new that we learn is a tricky kind of business, as we've learned from the history of GR itself. Sometimes GR hasn't worked to sort of comply with our intuitions that we had antecedently, and then a further study of GR actually showed us, oh, gee, we have to really revise our intuitions. So, for instance, most famously, in the case of singularities, physicists have assumed whenever space-time is singular, that can be ruled out a priori, because that's for sure not physical. That was Einstein's approach early on, for instance, and people accepted that. But then the history of GR abandonedly showed that some of the most physically important space-times are singular, so we cannot dismiss things like this as quickly. So a misclassification, is it a misclassification? Who knows? Maybe sometime, maybe just our concept hasn't been sufficiently clear beforehand. The other point you raised is very interesting, then that you demand that characterization of singular structure be extrinsic rather than intrinsic, and your conception is superior to the alternatives because it is. It labels singularness, I guess, as an extrinsic property. And here I would like to hear a little bit more about the motivation for it being extrinsic. Why is that a desirable feature rather than intrinsic? Is the idea that we've learned in dealing with singular space-time structure, GR, that we need to think of things that are somehow missing or some form of incompleteness, whether something is incomplete can only be judged by sort of trying to embed it in something more complete, in some sort of superstructure, and then see whether that works or not. And so, of course, whether there's an incompleteness in that sense depends on whether there sort of, exists something, sort of other parts of that space then, as it were. And is that the reason why I think it's desirable for singularness being extrinsic? So these are my comments and my questions. Thank you very much.
Thanks, Chris. You can take some time to reply and we'll move to Q&A.
Thanks very much for the comments. There's been a couple of points. I'll try to address at least some of them. It is. I recall it must have been a moment of late afternoon or late evening cowardice that I did erase the idea that I assume we're working classical GR, and I assume that I'm realist about singular structure. I think I got rid of the second sentence. The reason why I did that is because I knew we were going to talk about it anyway. But more seriously, it invites a lot of questions about whether we should be so in light of quantum gravity considerations that I don't want to discuss that much. The position I have is that there is no quantum theory of gravity so far. The attitude physicists have towards singularities vis-a-vis quantum gravity is actually a bit mixed. Most people think quantum gravity is going to get rid of space-time singularities, but the arguments they give for it are not necessarily very persuasive, it seems to me. There is, unlike in the case of various singularities in Newtonian mechanics, which were then got rid of by the quantum mechanical treatment, there is no empirical inadequacy with relativistic space-time singularities. And there are also those interesting theorems in semi-classical gravity by people like Aaron Wall, who do derive singularity theorems a la Penrose and Hawking from something like generalized second law of thermodynamics in the semi-classical regime. So the situation is not at all clear that quantum considerations will remove space-time singularities. And I think, having that in mind, it's a respectable position to say, okay, let me take classical general relativity at face value. They predict singularities, not only for interesting solutions, but also in a sense for generic solutions, at least so far as generic can be made precise by various singularity theorems of Hawking, Penrose, and then of course the others, because they still continue and the conditions are made weaker and weaker. Though interestingly, these predicted singularities are just witnessed by incomplete curves that are not necessarily curvature singularities. So that's my position vis-a-vis being realist about singular structure. And in this sense, I'm also not sure what kind of gloss I would put over the claim that singular structure shows the mathematical failure of the formalism. Sure, there is something like a breakdown of space-time. There is no well-defined space-time manifold at the point of infinite curvature, of course. In this sense, this might be a failure, or that they do disrupt physically reasonable motion, as I argued. But there is no failure in the sense that we know that there are experimental regimes which we can't describe using classical general relativity that we would otherwise could if we had those singular points. It's not clear to me that this must be so. Another question was about what does it mean to do physics at a singularity. So I think my answer to this is, the idea is that if you would have a well-defined mathematical object that would contain something like singularities as points, there would be interesting mathematical properties that you could describe, considering, for example, arbitrary neighborhoods of those singular points, how various fields transform when you move to the boundary, and so on and so forth. That might give you a reason to think that these mathematical physics results would have some maybe application to high energy regimes, insofar as you could show that these kinds of singularities are curvature singularities. So they do correspond to high energy regimes via Einstein field equations. Right? So that's what I mean by doing physics at a singularity. But then again, maybe there are other mathematical physics methods that would allow you for a similar thing that do not necessarily entail anything like the nominal conception. It's just hard to say in the absence of it. And the last thing I wanted to comment on was, so Chris mentioned the other proposal inspired by Manchak and Gare. So I have a slide in this later. It goes like this. So you can look at an open connected region, a U of Mg. So there's a bit of a further constraint that they put on what kind of regions can be singular. I mean, they meaning my projection of them into what they might think if they consider that question. If and only if every maximal extension of that region, when considered as a spacetime on its own, is singular. So two problems that I identified with this, the first one being more serious, is that I think it misclassifies some intuitive cases. By this I mean, it seems to me that there are cases which are intuitive to me that are not classified well by this definition, and we do not quite learn anything new about classifying them differently than our initial intuitions would do. And the example I have in mind is there are space-times that contain, there are so-called locally extendable singularities. So one example is if you have a Minkowski space-time and you excise a wedge of azimuthal coordinate, like a pizza slice, right? And you glue the things back together, you don't still have the origin. So that's an extendable, that's singular. The cone is a point which is singular, or where the point would be that would be singular. And it turns out that you might have open regions of that, open connected regions in that space-time that contain those incomplete curves that would hit the cone. And in this sense, I would say these are singular regions. And they contain, you take a closure of them, still contain those singular curves. But yet you can embed them isometrically in space-times where you actually add the point, which would be the cone point, and they would no longer be classified as singular in those space-times. So I think that's a general misclassification. Another problem is, sorry, it's the title, actually, being singular would be an intrinsic property of space-time regions in the Lewis's sense. I don't think being singular being an intrinsic property is a problem on its own. I don't think it's a kind of a priori desideratum that being singular should be an extrinsic property, and if you give me an intrinsic way of thinking about it, that's wrong. I think the reason why I was not happy with it being intrinsic is that not only would it be intrinsic, but also it would be a sense in which whether it holds of a particular region would depend on facts about wholly distinct spacetimes, namely those spacetimes into which you can isometrically embed it and whether they're singular qua spacetimes. So insofar as you think that being singular is somewhat of an elusive property, so that its analysis should also give you something like maybe a grounding story about what kind of facts ground the fact that the space-time region is singular or not. The story that, this intrinsic property would hold in virtue of wholly different possibilities strikes me as strange. I'm not going to use any other word there, and I'm going to pursue it any further. I think this is a weaker problem than the misclassification worry. I think misclassification worry is already kind of definitively puts this other definition. Thanks. These are my answers.
Okay, great. So we have time for questions. If you have a question, please raise your hand, and then I'll go through. Start on session.
Yes, thanks both. This is kind of maybe a history question. The term singular, or when physicists say a theory has a singularity, sometimes they say that in other theories, like electromagnetism, like theories where the term singularity just seems to mean something like it blows up, or the energy, or some property is maybe defined, but the point exists. is a space-time point at which the property, whatever property it is, kind of it's ill-defined or something like that. And I was just wondering, like, from a maybe more historical perspective, if I mean, because singular is a technical term, right? It's not like, I mean, at least in this context of physics, and I was wondering if you think there was a shift when people moved from, say, I don't know, other theories to general relativity in how they were thinking of the term singular, or what's going on there, because I don't know, this is based on a theory in this sort of context, right? Or maybe they do that in a different way. So I'm wondering if you have something to say about that.
I wish I had more to say about this from a historical perspective. I mean, it is true that singularities in physics are often just thought to be some kind of divergence of a field value over some base space. So usually you would think, well, if I have a singularity of the electromagnetic field over space-time or something going wrong with the physics I have there maybe, or maybe I just sometimes might just use them for modeling purposes, like modeling wave shocks or whatever. So it depends on what kind of attitude you have towards what is supposed to be represented by the formalism that you're using. And it is the case that the situation is different for space-time singularities, precisely because you will have that there won't be a point in the fixed background of space-time at which you will have an ill-defined value of the metric field. There will be just no point there. So this is a clear difference. This is also why space-time singularities are so tricky to analyze, and so tricky to explain away by just, oh, there's some kind of idealization of physics going on, there's some kind of failure of modeling maybe, or something like this so easily. So I mean, I've just said, I agree there is a distinction. I think this case is more difficult philosophically. There are also cases of the first case of singularities that arise in relativity too. They're described very nicely in the Stanford Encyclopedia entry on singularities in black holes by Eric Curiel. But I did not treat them here, and I don't treat them in the paper. There are some references on the historical perspective, but I'm not sure I can tell you a lot of interesting stuff. I mean, perhaps, but this is just not a very educated guess, but this earlier understanding of singularities as infinities on the background space might have been, to some extent, maybe a reason why Einstein was so queasy about them, and why he hated the idea that there might be something like a singularity in solution to his field equations. So he thought that this is some real kind of failure that has to be fixed. But then, of course, I mean, since the singularity theorems of Penrose and Hawking, no one thinks of it anymore.
Other questions? Yeah, yes.
Thanks. I don't know how core this question will be to your project. At one point I was a little bit surprised about the definition of localizability, and in particular that it puts this huge emphasis on the distinction between having having a compact closure versus non-compact closure. Can you go to that slide? Right. You might think whether a property, for example, take a time-bounded slice of Minkowski space-time. You might think whether a property can be associated with a region that is at the future bounded by the boundary of this slice of Minkowski space-time, but spatially infinite, or it is temporally bounded but spatially finite. I'm not seeing why that makes philosophically such a big difference. I was thinking, if we wanted to develop a notion of localizability in kind of the direction of whether we would want it to be some sort of limiting motion, where maybe we can, property is localizable if we can attribute it to smaller and smaller regions, something like that.
Sure, thanks. Yeah, so I think the motivation here with using compact closure is it's a fairly natural topological way of making sense of smallness, in the sense of, well, you will always have any way of covering with open sets will have a finite subcover. You can define partitions of unity easily, though I mean you can do it in paracompact manifolds anyway. But so the region you described by time-bounded but not space-bounded bit of Minkowski, that's not relatively compact, right? Because you have
It's not compact.
it's not compact. Yeah, I mean no open region is compact. That's why I talk about no proper open region is compact in relativistic spacetime. That's why I talk about compact closures. But that's it, right? And so the idea you had about limiting process of regions being, say, proper subregions of them, and then being localizable. Yeah, I thought a little bit about kind of making these things precise using notion of filters, but I got nowhere. So maybe to say what I think. Okay, sorry, I'll take a step back. So in the presentation, in the paper, I don't associate localizability with smallness in any sense. I associate localizability with a determinate fact of the matter whether any particular region, which is arbitrarily small in any way of making sense of small you might have, is singular or not, and identifying a singular region in space-time gives you a positive test for a singularity of the whole space-time. Right? In this sense, this is localizability I need. Now there's a further question. Okay, is it the case that for any singular space-time, I will have a singular region that is in a sense small? Maybe, I know, a limit of singular regions or something like this. Now, this has an intuitively plausible idea. I tried to make this precise with filters. I couldn't. Boundedness is not an option because, as I said, Lorentzian metric doesn't define a standard distance function, unlike Riemannian metrics. The trouble with looking at compact closure is that if you excise a point from your set in, say, Minkowski spacetime, any causal diamond, whatever, it no longer is relatively compact, because compactness is just same as sequential compactness for topological manifolds. So the idea I had was, the formal thing is, you can look at certain bounded subregions of the frame bundle over the spacetime manifold with a certain class of Riemannian metrics that are definable on it up to uniform equivalence. These are called the Schmidt metrics. They were used by Schmidt when he constructed the B boundary, but that's without the B boundary thing. You look at bounded subsets in the frame bundle, and you can prove that for any singular spacetime, for any singular region in any singular spacetime, it will have a subregion that is the image of some bounded Cauchy incomplete subset in the frame bundle. There is a very lovely theorem by Hawking, Ellis, and Schmidt from early 70s, which is thought to be kind of partial Lorentzian surrogate of the Hopf-Rienev theorem in Riemannian geometry. So the Hopf-Rienev theorem says, whenever you have a connected Riemannian manifold, it is going to be geodesically complete if and only if it's Cauchy complete as a metric space, and if and only if it has a Heine-Borel property. So every closed and bounded subset is compact and vice versa. Now, Hawking, Ellis, and Schmidt prove that a space-time is B incomplete if and only if the orthonormal frame bundle over that space-time is Cauchy incomplete with respect to any choice of that natural Riemannian metric on top of it. So there is some kind of relationship between Lorentzian geometry and metric geometry if you look at those frame bundles, but honestly, this is a mathematical result that you can kind of spit out. I'm not sure what's the physical relevance of it vis-a-vis the concept of localizability, just because physical significance of those Schmidt metrics is a bit opaque to me. It's nice that they're definable basically just from the Lorentzian manifold structure. Because, I mean, we have some time, I can just talk about it. The idea is that because you have parallel transport on your spacetime, you don't have a free choice of the connection on the bundle. It just chooses the connection for you. So you define these metrics on the frame bundle basically using just the structure of the spacetime, which makes it nice, but again, haven't seen it applied anywhere in a kind of more physical setting. So that's kind of where I am on these issues technically.
Okay, are there any further questions? If not, please join me in thanking our speaker.